6.3 Applications of the mean value theorem. If the graphs of two functions have identical slopes at each number in an interval, then the functions differ by a constant on that interval. What this says, every single point, this point here, this point here, this point here, and this point here. The slope here is the same as the slope at that point. Slope at this point is the same as the slope at this point. Slope at this one's the same as the slope as this one, and the last one's the same as this one. That means the curves are identical. The only thing that's different is one has been shifted up or down compared to the other one. So they're different by a constant. If a graph has shifted up or down, what has changed? What's changed on this graph? Y. Got the y-axis. The y-intercept has changed. This one's down here. This one's up here. It's been shifted. I don't know which one's the original. If I call this one the original 1 and this one's the second, it's moved up. The y-intercept has changed. What this says, I just copied this directly out of your book so I didn't have to rewrite it. Yeah. What this says, if f is continuous on an interval I, if f prime exists and is equal to 0 for each interior point, then f is constant on I. If f and g are continuous on an interval I, and f prime and g prime exist and are equal for each interior point of I, then f minus g is a constant on I. All this is saying I have two different graphs. Both graphs, both their derivatives are identical. So that means all their slopes are the same. The only thing that's different is a constant being added onto the second one. So if a function is defined on an interval, then any continuous function of f on I such that f prime of x is equal to f of x. For each interior point of I, this is called the antiderivative. So instead of doing derivatives, we're now going to start working with antiderivatives. Anti means opposite. So if I took the derivative, f of x, and define f prime of x, if I had x to the fifth, what's the derivative of x to the fifth? 5x to the fourth. I need to find the antiderivative, so I need to find the opposite. So I'm going to find f of x. What did I really do here to go from x to the fifth to 5x to the fourth? What do I do to find the derivative? Put the exponent out front. So what's the exponent doing? Multiplying. So if it's the opposite, it would be dividing. So it's going to be dividing. Now, before I do that, what did I do with the exponent? Minus 1, so I have to add 1. So instead of 5, I'm going to have 6 divided by 6. Okay, take the derivative of x to the 6 over 6. If I took the derivative of x to the 6 over 6, the 6 comes out front and it becomes a 5, right? What's 6 over 6? 1. I get back to normal. And the only thing that's different is now we put a plus c.
So do you add first, then divide?
Add first, then divide. No. Gabby said divide or move the exponent out front, so that's why I just said divide. And it's always plus c when you work backwards. The reason why, what's the derivative of any constant? 0. So, x cubed is an antiderivative of 3x squared. Sine of x is an antiderivative of cosine. Any antiderivative x cubed plus c will be any antiderivative of x or 3x squared. Sine of x plus c is the antiderivative of cosine. Work backwards. The derivative of what gives me cosine? Sine. You're working backwards in derivatives. That's what you're doing. If it was negative sine, the antiderivative would be cosine. We're going to find the antiderivative for x squared plus 4x. All right. Derivative or antiderivative of x squared. It would be x cubed over 3. Because if I took the derivative of x cubed over 3, the 3 goes out front, 3 divided by 3 cancel out, I'm left with x squared. What's the antiderivative for 4x? Don't even worry about the number out front. What's the antiderivative of x? X squared over 2. And there's a 4 out front, plus 2x squared. All you do, go through this again. What's the exponent here on the x? 1. Add 1 to it. 2, and divide by that number. There's a 4 out front, so the 4 is still out front. What's 4 divided by 2? 2. Plus c. And that's your answer. Plus c. Secant squared of x. Now, it's better unless you have them memorized. Look at your sheet that has all the trig identity derivatives. What gives me secant squared of x? Whitney? Tangent of x plus c. That's it. For the trig identities, just look on the chart. What gives you that? What's the antiderivative of e to the x? What's the derivative of e to the x? E to the x. So what's the antiderivative of e to the x? E to the x. It stays the same. Okay, we're going to find the function of f such that we have f prime equals cosine of x and f of pi over 2 is equal to negative 1. We're going to find the function of x. We're going to try to, or what's the antiderivative of cosine? Sine. So it's sine of x plus c. Do you see what I did? We know that f prime is cosine of x. So to find out what f was, I took the antiderivative. Now I know that f of pi over 2 is equal to negative 1, right? So I have sine pi over 2 plus c. This right here, that's what we know up there. So negative 1 equals, what's sine of pi over 2? What's sine of pi over 2? Use your calculator, use your wheel, or your unit circle. So what's sine? Sine is 1. Now I need to subtract the 1 over. Negative 2 is what c is. So the original function was f of x equals sine of x minus 2. What we did is we went through and found out what c was. Questions on this problem? You're given the derivative. So to find out what the original function is, you take the antiderivative. But when you take the antiderivative, you get a plus c. This tells you f of pi over 2 is equal to negative 1. So I set it equal to 1. Find out what sine of pi over 2 is. That's 1. This right here, that's just letting you know. All right? You don't need this right there. I just put it so you understood where that pi over 2 came from. So it's 1, solve for c. C is negative 2. There's the antiderivative. Instead of writing c, I write negative 2. We're going to find the interval in which f of x equals 2x cubed plus 3x squared minus 12x minus 3 is increasing and decreasing. That is the original.